In the previous lecture, we arrived at this equation through the modification of one of the kinematic equation and using the concept of the net force being the sum of a tangential force and a centripetal force. In this equation, Ek stands for kinetic energy, which is equal to mv squared over 2. F net parallel is the component of the net force that is parallel to the trajectory. The sign of this component results from the comparison with the direction of the tiny vector displacement delta d. The restriction of delta d being tiny was to ensure that the net force was considered essentially constant during this displacement. The first equation shown here indicates that a change in kinetic energy occurs when both delta d and F net parallel are not zero. The product of the parallel component of the net force with the magnitude of the displacement is called the work done by the net force and labeled W net. The concept of work is not restricted to the net force. It can be defined for any force acting on an object during a displacement, but only the net work is equal to the change of kinetic energy. This definition of work might not fit with your everyday use of the word work. For example, carrying a heavy suitcase along a flat terrain by exerting a vertical force to keep the suitcase off the floor might seem a lot of work. But this situation involves an horizontal displacement and a vertical force, so the component of the force parallel to the displacement is 0. According to our definition of work, you are not doing work while carrying a heavy suitcase. By comparing each external force exerted on an object having a displacement, you could define each of their parallel components to that displacement. The sum of these components must be equal to the parallel component of the net force. Let us multiply by the magnitude of the displacement delta d on both sides and multiply the magnitude of delta d inside the brackets. Using the definition of work, we can write this equation, which means that the work done by the net force is equal to the sum of the work done by each of the external forces acting on the object. Here is our definition of work. Just like kinetic energy, work is a scalar. It can be positive, negative, or 0, depending on the sign of the parallel component of the force. Since it is the product of a force and a distance, the measurement unit could be thought as a Newton meter. Reverting to the basic SI unit, a Newton is a kilogram meter per second square, which means that a Newton meter is the same thing as a kilogram meter square per second square. We know this combination of units to be a joule. So work has the same measurement unit as the kinetic energy. With its multiple steps, this example will be a good practice for evaluating the work done by individual forces, their relationship with the net work, and the change of kinetic energy. It involves motion along an incline that makes an angle theta with the horizontal. A box of mass m is to slide down the incline, so it will go through a displacement delta d along the incline. This is the trajectory. The free body diagram involves the gravitational force, the normal force, which is perpendicular to the surfaces touching, and a kinetic friction force. No information about the coefficient of static friction means that we are to assume that it was not high enough to stop the sliding. We will use this set of reference directions, chosen so that the x reference direction is in the same direction as the displacement. Since all external forces involved are constant, we can use our definition of the work established with a kinematic equation valid for constant acceleration. The list of givens is the mass of the box, the magnitude of the displacement, the angle that the incline makes with the horizontal, the coefficient of kinetic friction, and the initial speed. The first part of this example is to evaluate the work done by the normal force. The equation for it is this expression. But because the displacement is along the incline and the normal force is perpendicular to the incline, there is no parallel component of the normal force, which means that the normal force is not doing any work. The second part is about the work done by the force of gravity. This time there is a parallel component for the gravitational force, as you can see if you create a right-angled triangle that uses the gravitational force as the hypotenuse. This triangle is similar to the one describing the incline, and a bit of geometry indicates that this angle is also the angle that the incline makes with the horizontal. The side of the triangle opposite to theta has a length proportional to the magnitude of the parallel component of the gravitational force. Since that parallel component is in the same direction as the displacement, the component is positive. The trigonometric ratio that uses the opposite side and the hypotenuse is sine theta, which means that we can write FG parallel as FG sine theta. Replacing FG with mg gives this equation. Next, we can substitute the givens to be able to arrive at the final numerical answer. The third part of this question is to evaluate the work done by friction, which is expressed this way. According to the free body diagram, the friction is along the incline, but in the opposite direction to the displacement. So, the parallel component of the friction force is negative and equal in magnitude to the product of the coefficient of kinetic friction and the magnitude of the normal force. To evaluate the magnitude of the normal force, we have to look at the balance of forces in the y-hat direction. There are only two forces that have y components, the normal force and the gravitational force. Since there is no motion in the y direction, the y component of the net force is 0. The normal force has a positive y component equal to the magnitude of the normal force. To evaluate the y component of the gravitational force, we need to refer to the right-angled triangle where the magnitude of this component is the adjacent side of the triangle. Using the trigonometric ratio cos theta, we can express the vertical component of the gravitational force as minus Fg cos theta, recognizing that this component is in the opposite direction to y hat. Next, we can replace Fg with mg to get an expression for the magnitude of the normal force, which can be substituted in our equation for the work done by the frictional force. It is time to make the substitution of numerical values and use the calculator to find a numerical answer. The next part of the question is about the evaluation of the net work, which is the sum of all the work done on the object by external forces. You might be tempted to just add the previous three answers, but here I will take the time to write the expressions with the variables once again and factor out common quantities in the two non-zero terms. Substituting the givens again leads to this expression, and the use of a calculator leads to this answer. Now on to the next part, which is about evaluating the final kinetic energy. The change of the kinetic energy is related to the net work, and the definition of change is to subtract the initial kinetic energy from the final kinetic energy. Fortunately, since the box was not moving at the start, its initial kinetic energy is 0, which leads to this simplified relationship. Since we have already evaluated the net work, the final kinetic energy is 19 joules. The final part to this question is to evaluate the speed at the bottom of the incline. Here is the equation relating kinetic energy to the speed. Isolating for Vf gives this expression. Since EKF is equal to the net work, we can substitute the expression for the net work into the last equation and remove the mass from the expression to give this. Supplying the numerical values for the givens similarly to what was done in part D leads to a final answer of 3.5 meters per second. Now, in order to finish this problem properly, let us summarize our final answers. We evaluated the work done by the normal force, the work done by the gravitational force, the work done by the kinetic friction force, the net work, the kinetic energy at the bottom of the incline, and the speed at the bottom of the incline. There are some forces in nature that are special in terms of the work they do and in terms of their relevance to the subject of energy. They are called conservative forces. They will be the subject of the next installment.